In this video, we're going to look at basic transformations with graphs. We're going to just focus on horizontal shifts, vertical shifts, and reflecting about the x-axis or reflection, and so flipping the graph over. So there's more to transformations. We're not going to look at vertical stretches or compressions or horizontal stretches or compressions, but knowing this really helps when you look at graphs in general, and just knowing the basic shapes of the graphs for pattern recognition. If I first look at the first thing, if I'm talking about horizontal shift, that means I'm messing with the x-axis, right? The input values are the x. So if I was given just our basic graph, we'll look at, say, f of x equals x squared. That's the quadratic, the basic quadratic graph. Then f of x equals x minus c quantity squared actually shifts the graph c units. So it does the opposite of what you'd think when you mess with the inside. So what I mean by that is I'm messing with the inside, so I'm expecting to have a horizontal shift. I'm messing with the x. It looks just like this graph, but I'm subtracting c, so I'm going to shift it to the right c units. So when you mess with the x value, you shift left or right along the x-axis. It always moves the opposite of what you'd expect when shifting horizontally. So an example would be g of x equals x plus 3 squared shifts the graph of f of x equals x squared to the left 3 units. You would think to the right because it's plus 3, but it's actually the opposite when you mess with the domain values of the inside. So we're messing with the inside, the horizontal shifting does the opposite. So let's look at that with Desmos. So if I go to Desmos and I say, I'll type in, here's just your basic x squared graph. Okay, and now let's take that graph and let's graph one just like it, but we're gonna say we'll add 3. So it looks like I would move to the right 3 units, but I'm actually going to move to the left 3 units. And so when you add 3, so if I added 5, I'd move to the left 5 units. If I subtracted 3, I would move to the right 3 units. And so it just does the opposite of what you think when you mess with the x. And notice that they're the same graph. So if you know your basic graph functions, it's really nice. By transformations, you can just know which way they shift. So now let's look at a vertical shift. Vertical shifts do what we would expect. So when we're looking at a vertical shift, if I look at that basic function again, f of x equals x squared, then g of x equals x squared plus c, I'm adding c to the overall function, or the y, or the output. So that means I'm going to shift the c units vertically, and it actually does what you would expect. So if I had example g of x equals x squared minus 3, it's going to shift the graph down 3 units, the original graph down 3 units. So let's look at an example of that. So I'm just going to say, take my x squared, and then I'm going to say I subtract 3. It's just going to take the x squared graph and drop it down 3 units. Or let's mess around with it, try adding 1. I'm going to bump it up 1. Let's try adding 3, bumps it up 3. So whenever you mess with the outside of the function, the overall function, you're messing with the vertical or the output or the y variables, and it does what you'd expect. And so that's helpful when we're looking at graphing these. The last thing is, what about reflection? So reflection is if you ever negate the whole function, you're changing the output values, and so you're changing the sign of all the output values, the y's, and therefore it flips the graph. And so a quick example of that would just be, let's look at Desmos again. Let's just look at our basic x squared graph, but what if I negate it on the outside? It just took it and flipped it over, or reflected about the x-axis. And so we'll look at different things now, or a combination of both of those, and the examples are on the practice test have that. So what if I had something like examples 4 and 5 in the chapter 12 practice test? If I'm given a function, it looks just like the absolute value, the v-shaped graph right here, f of x equals absolute value of x, and say that's the basic function. What would this function, f of x equals negative absolute value of x plus 5 minus 7, what would that actually do in words, transforming it to compared to its basic function? Well, part A Yeah, I mean, for part A, it says reflects about the x-axis. Well, I expect to do that because of the negative. Does it shift right 5 units? I disagree because of the plus 5. It would do the opposite of what you'd think when you're messing with the x. So that's gone. It's actually going to be B. It does reflect about the x-axis because of the negative, and it shifts left 5 units. It does the opposite of what you'd think when you're messing with the inside of the function, or the horizontal shift is the opposite of what you'd think, and then down 7, the outside. You're messing with the outside of the function. It's what I would expect, and so that is one way I would ask that kind of a question. Then also, if I gave you a function itself, and I said identify which graph goes with this function, you'd be able to do that. And so the circle, as you said, circle the function, circle the graph of this function, g of x equals, well, I know it flips over, so it should be an upside down parabola because it's an x squared, and so I'm thinking upside down, so I could eliminate a. That's not part of my, that's definitely not it. And then minus 2 means I have to move to the right 2 units because it does the opposite of what I expect when you're messing with the x. So I could throw away C and B, so it has to be D, and then plus 4 bumps it up 4 units. So the original graph takes the original x squared graph and bumps it to look like D. So knowing that pattern recognition is really helpful. So that is graphing by transformations. We're going to mainly focus now on quadratics, just the x squared type graphs, and we're going to look at how we do a comprehensive graph of those next.